and Signal Processing, which is organized by the Department of ECE, VITW College. It is my immense pleasure to introduce you to the session. The coordinator of this Atal FDP event, Dr. T. Vishnupriya Madam, HOD ECE VITW, co-coordinator of this event, Dr. T. Hemlata, my colleague, and I myself, Roja Mugula, assistant professor from the Department of ECE, Vijay Institute of Technology. First and foremost, Srinivas sir, it is my immense pleasure and honor to introduce you to our congregation. With your permission, I would like to read out your profile, sir. Please allow me, sir.
Yeah, thank you. Please continue. You're able to hear me? Hello?
Yes, sir.
Yeah, let us continue.
Dr. Srinivas Talabatula is professor in EC Department, Indian Institute of Science, Bangalore. He obtained BSc Honours in Physics from New Science College, Hyderabad, and ME Integrated and PhD from IISc. Sir is a postdoctoral research fellow at Toyohashi University of Technology, Japan during 1992 to 96. His area of research interest is optical communications, in particular photonic integrated circuits. Sir published about 150 papers and guided 42 PhD students till date. He is a member of the National Board of Accreditation NBA and the chairman of GATE IISc Zone during 2010 to 13. He is an active volunteer in IEEE Bangalore section and was the chair in 2024. Earlier, Sir is the chair of IEEE Photonics Society and IEEE Communication Society Bangalore chapter. Sir, once again, we welcome you to the session and I hand over the mic to you on your speaking note on photonic ICs for quantum computing. Thank you, sir.
Good evening, everyone. I'm very happy to take part in your FDP and speak on this topic on photonics for quantum information technology. I hope everyone is able to hear clearly, and I will request the organizers to interrupt me whenever necessary. I have my cell phone also switched on. You can call me on that if there is any network interruption or anything like that. So first of all, this talk, and I hope most of you will find this topic interesting. I know I have seen that you have been doing a lot of quantum in this FDP. Already many of these initial slides you may be already familiar. But I would like to make it from a conceptual point of view, and I hope it will also be useful. So before I go further, I'll acknowledge my students who have done research in this subject and who have made the slides for me and so on. So this is a brief outline of my presentation. So we'll go up to about more than 1 hour, 15 minutes or so, and we'll have a lot of questions. So we'll start with a brief introduction, then history of quantum. You see, I have named it as quantum information technology. This can include a lot of things. As you may be observing in the FDP also, the word quantum is used in a very generic sense. So we can say that quantum information technology is a subject which can include quantum communications, quantum computing, and all those things. And also, I also noticed that a lot of new areas like AI, then photonics, and all these things are being combined with quantum. So it's a very interesting subject, as I mentioned in the initial my 5 minutes speech. There's a lot of interesting things around for us. So let us get more and more conceptual. In terms of this FDP, I would request everyone to understand things conceptually. A lot of details are there. Details you can learn gradually using the papers and also the books and so on and so forth. But we should carefully understand what is the main point in each of these presentations. That's what I would request everyone to focus on. In this presentation, we'll focus on using photonics for quantum applications. That is the main idea. And also, we also put the other keyword, the information. We are talking about the quantum information. When you look at the literature, you will find a lot of quantum, about half of it quantum devices like single photon sources, photo detectors, and all those things. And then the other half is more onto the computing, communications, and so on. So our focus this time will be a mix of these two. That's what I would like to put the setting. Okay. So we'll start with a brief history of quantum computing. Then we'll see what are qubits. We would already seen that, but I'll put from my own point of view. Then we'll see a few systems like quantum gates, and then block diagrams of quantum computers, quantum communication link, and a lot of integrated photonics. I'll show you later on in these slides. And a little bit of work that we have done in our lab also, I will include in this. We have done a few theses, 3 theses we have done on this subject until now, and I'll show you them also. But as I mentioned in the beginning, in India, there's a lot of interest in this subject, and a lot of progress has to be done. Globally, also, if you see, a lot more things to be achieved. See, I would like to mention that there is a rival technology called electronics. So, all these things that we have been doing in electronics now, people are thinking to do in photonics in near future. And also, quantum is a new subject which tries to revolutionize our communications and information technology. So photonics will play an important role there. That is importance of photonics. I'll repeatedly mention some of these as we get going. So let us look at very briefly 1 or 2 slides on what is meant by this photonics. So photonics can be considered as the science and technology involving light. As you know, light has got the wave nature as well as a particle nature. It appears both sometimes, and sometimes it appears none. So this is a very strange thing that photonics has. And of course, we are not going into the quantum basic, very fundamental properties, but we can say that the subject of photonics is analogous to electronics. See, electronics also we use very loosely. The device and systems based on electrons. Electrons are the basic units which are involved in the functionality of these devices. That's what we call electronics. Electronics is based on electrons. Similarly, photonics is based on photons. Photons also are fundamental particles like electrons. Actually, they are called bosons. And a lot of, if you look into um, the particle physics, then you will have know a lot of properties of the photons. We are not interested in that right now. So we can just now say that they are bosonic in nature compared to electrons, which are you use Fermi-Dirac statistics in electronic devices. We use Fermi-Dirac statistics. In contrast to that, we have to use Bose-Einstein statistics to study the properties of photons. So all the information processing tasks that we have been doing in electronics, people have attempted using photonics. For example, you can do in the information technology, we use signals, you generate signals, you transmit, you control from one point, transmit from one point to the other, you control the light propagation, you can do this optical signal processing, you have to display this information, and you have to sometimes you have to also store a lot of information. So all these operations people have been doing using electronics. In fact, we can say that we are living in the world of electronics, right? Still. Hmm? Because all these devices that we see around, like the laptops, the cell phones, the TV, these are all electronic devices. Electronics functions are important there in that. But there are also indicators of what photonics can do. See, after the invention of laser in 1960, the lot of photonic optical technology has developed. For example, there are biomedical applications. Now, you know, a lot of surgeries are being done by using lasers. And you are all very aware about the fiber optics revolution. The present day broadband revolution has been made possible just because of fiber optics. Now there are fiber optic links all over the world. We have the national backbone network. These are all the indications that what photonics can do. That is an indication in the communication area. See, in olden days, you are very confined with very small data rates, like a few Mbps or so. Now we are going to several Gbps. That is the revolution that has been made possible because of fiber optics and, of course, photonics. So there are a lot of things to come in photonics. A lot of technological development is happening. Then, as you can observe, a lot of academic activities there. Almost in every university, there are photonics programs. Like in IITs, IISc, etc. A lot of people are doing the research, and of course in other universities also. And you see, there are national programs. Indian government has got a national program on photonics. Similarly, almost every country has got national programs on photonics. So the importance of photonics for quantum is what we'll highlight in this lecture. And many of you also know there are a lot of courses people have been trying to introduce into your curriculums in BTech programs and so on. At least some of you people, you must have already noticed that there are programs on quantum computing, quantum communication, etc. So these will automatically involve optical technologies. So that is the importance of photonics. I will highlight more and more as we go along. So let us get going with the quantum information technology first. Then I'll show you a little bit of photonic integrated circuits, and then we'll go further. So the keyword here is a quantum. See, sometimes you call quantum mechanics, sometimes you use the term quantum physics. These are almost the same, even though there is technical difference. So let us assume the quantum is an important element now. So our main idea when it comes to quantum is that when you go to smaller and smaller dimensions, you have to consider quantum phenomena. That's what we have in mind. We think that quantum comes when it is very, very small dimensions, like atomic dimensions. But then most of the phenomena that we see around, like the light, for example, or the colors of the objects, or a lot of phenomena, strengths of the materials, these have all been made possible just because of the quantum effects, not the classical effects. See, about 100 years ago or so, this quantum was not there. People have been understanding using the classical effects. So the opposite of quantum is the classical. So we should make up our mind to understand things in the modern way. That involves quantum. So a quantum computer is a computer which involves quantum phenomena. Or maybe I will not use the word now. Later on, we'll talk about qubits. So quantum communication involves transmission of information, maybe classical information or quantum information, from one point to the other point. Those are the very crude, very basic definitions. So you can say that everyone has mentioned, I suppose, in the first lecture also I have seen, Richard Feynman is the one who has envisaged that you can do computations using quantum. We are all familiar with mathematical operations like multiplications, divisions, doing some calculus, solving some equations, differential equations. These are all the things that we do in computing. And you know that we are using classical computers. Classical computers is based on the circuit theory. See, electromagnetic theory and circuit theory is also considered somewhat classical, even though it is not fully classical like mechanics. But we can say we have been using classical principles for computing applications. What Richard Feynman thought was you can take up a quantum phenomena and see what is the mathematics behind that, and then you can say that we are solving that problem. It is not the same as classical computing. So real quantum computing means we should take a quantum phenomena and then see what is the mathematics behind that and see what it is solving. That is the basic difference, according to me, between the classical computing and quantum computing. So you can go finer detail into that because from computer science point of view, you know what are the different techniques that we use, algorithms that we use for calculations and computing and so on. Similarly, we can arrive at techniques and algorithms for computing using photons. So sometimes people call it as quantum supremacy. Quantum computing, which cannot be done by classical, is sometimes used as a quantum supremacy. Of course, there is also another important thing that he has already announced, that this quantum phenomena will limit all our electronic devices. So the electronic processes like the delays in CMOS circuits or gate widths or the lithography, dimensions in lithography, these are all limited by quantum effects. You cannot go beyond certain limits. That's one of the important announcements that he has made. But in this context, it is important for us to recall that he has mentioned that we can do computations using quantum effects. So this is a brief timeline of quantum information technology. So starting with the Feynman's idea, the next came one of the earliest protocols called BB84 in about 1984. Then there are a lot of algorithms that people have developed. Like, for example, you can see Shor's algorithm. It can factorize very large numbers. That shows that it is possible to do large computations by using that we can that shows that we can do large computations using quantum. And then there's also what is called this Grover's algorithm for searching very big databases. So if you want to search for some data, you can use Grover's algorithm, does in a quantum way very efficiently. So there are a lot of other models that people have developed. The progress of quantum technology, if you see, a lot of things are there, like models of quantum computers, models of quantum communications, analogies of electronics computers, and so on. But let us jump to 2016. About 10 years ago, China has launched its first communication satellite, Mesius 1. They have transmitted quantum information from China to Austria in Europe using laser beams. So that is one of the see that is, of course, people have done earlier some of these, but this has attracted a lot of attention, and all over the world there's a lot of interest in quantum computing. This can be one of the milestones, you can say, or one of the influencing events in quantum computing or quantum information technology. Then, of course, a lot of other satellites many countries have launched, and every country has got a program on quantum. And of course, in the recent times, you must have seen big companies like Google, HP, IBM, and all these people are into the quantum bandwagon. Mm. So they are trying to improve and develop newer and newer techniques and so on. But I would like to mention that the quantum computing or quantum information technology is waiting for a breakthrough in the technology. Why don't we have a quantum computer still? See, if you look at the quantum computer created by IBM, for example, it looks like a very big unit, like the olden days of ENIAC computer. For a few qubits of computing, you have a very big system. A lot of it is taken by the control, then the temperature control, and so on and so forth. So, if we look at if from a technical point of view or from a common man point of view, if you look at it, we would like to have quantum functions on a small chip, like what we have with VLSI circuits. Why do you think the electronics has progressed so much? Because of the VLSI. That's where comes integration of all these functions onto a small chip. We do not want to have a quantum computer in an optical table. Okay, for some special application, it's okay. But in general, we would like to have a quantum chip in our wristwatch or in a laptop. So, will it be possible? Is an important question. And the answer seems to be yes. So, we need a breakthrough in technology, particularly the photonics technology, where you can make all these components necessary on a small wafer, similar to VLSI. That's what we can hope in the near future. But of course, it will take time, about 10 years or so, we can say. Meanwhile, people will try to develop a lot of algorithms and try a lot of simulators based on the existing computers, and also a little bit on the cloud. Some elemental forms of quantum computers also, whatever these people are developing, may be used to do some quasi quantum computing, we can say. So let us get to um, what are the qubits. I think it's already been mentioned by other speakers. You can say qubit is the basic unit of quantum information, analogous to bit in the classical information technology. Just very quickly to recap, in classical information technology, we use very definite values for 0 and 1. For example, 0 is represented by 0 volts, 1 is represented by 1 volt. This is very easy. We can say definitely, we can say this is 0 bit and this is 1 bit. So in contrast to that, in quantum, excuse just a minute, please. So sorry for the interruption. So we are talking about the qubit, nature of the qubit. We are going to compare with a bit. Already people have mentioned, I suppose in the first lecture itself, I have seen. So in the quantum information technology, we have to use some objects like atoms or photons. Let us say, because we are talking about photonics, we'll use photon as an object to represent qubits. There are several properties of photons which we can use. For example, we can use the polarization. You have horizontal polarization and vertical polarization. If you take a light wave, we can say horizontal polarization to represent 0 bit and vertical polarization to represent 1 bit. You can transmit a sequence of optical pulses, and then you can say 0 and 1s. This is a classical. Now, if I want to use photons, which are, you see, we said when we go to very smaller and smaller level, atomic level, the quantum properties become important. So photon has got several quantum properties. One of them we'll say is the polarization. So we can use horizontal polarization for 0 qubit state and vertical polarization for 1 qubit state. So what is the problem? The most important problem with quantum objects or quantum with the quantum nature of the objects is that parameters or the characteristics are not well defined. For example, horizontal polarization of a photon is not well defined, or the vertical polarization of the photon is not well defined. What is defined is their probabilities. Probability of photon being in the horizontal polarization will be so much. Probability of photon being in the vertical polarization will be so much. That is what can be said. That means we don't know exactly what polarization photon is in. For example, it can be in 45 degrees polarization. But that also not very definite. We cannot say definitely. We can say that it is in 45 degrees polarization with certain probability. So whenever we are talking about probabilities of objects with respect to some parameter like angle, there is a probability distribution function. You can consider horizontal polarization, there is a probability distribution function. That means with 0 degrees, there is a probability P1, 1 degree probability P2, and so on and so forth. You imagine a Gaussian sort of distribution for the horizontal polarization. So this is a probability. Similarly, vertical polarization also, you have a probability distribution function, a different one maybe. Similarly, at 45 degrees. So the exact polarization of the photon cannot be exactly specified. That's the most important um, idea or most important property of the photon and the qubit. The state of the object cannot be defined well, but only with respect to a probability distribution function. How do we get the probability distribution function is an important question. So if you go back to quantum physics, you know the quantum properties in one of the formulations, you can say as the Schrodinger formulation, there is a Schrodinger's equation. So if you solve the Schrodinger equation, you get the wave function psi. And the square of the psi is interpreted as the probability distribution function. That means, unlike in the classical domain, in the quantum domain, we have to discuss about the probabilities. See, earlier, if it was a classical light wave, we said that the electric field vector has a value so much exactly along horizontal direction, so much value along y direction. This we are able to say exactly. Whereas in the quantum description of the photon, we are not able to mention whether it is whether the qubit is in the zero horizontal polarization state or vertical polarization state or any polarization state. But as you know, the actual polarization state of the photon can be described as a linear combination of the horizontal and vertical polarization states. And whenever we are talking about these probability distribution functions, you have all these moments. For example, average of the PDF. So the whatever notation that you are familiar now, the zero ket implies it is an average of that wave function. Ket 1 is average of the vertical polarization. That is a probability. It is giving a probability. Okay. Similarly, the actual state of the photon is psi ket, the average of the psi ket. So you can say that is a linear combination of 0 ket and 1 ket. Alpha and beta are the coefficients. So we should go back once again to the Schrodinger, which says that psi is a complex quantity. See, I would like to recall. Let us spend 1 or 2 minutes like this. See, in the classical domain, when you solve the electromagnetic wave propagation, we have the wave equation. I suppose many of you can recall wave equation. So the wave equation the solution of that wave equation actually is real, but we use complex variables to understand that. So the wave function or the field quantity is given by a into e power I omega t minus beta z. That means we are using complex variables to study the wave propagation. Similarly, when you solve the Schrodinger's equation, you come you result mm, in complex quantities. Psi is a complex quantity. So linear position of 0 ket and 1 ket can involve alpha and beta, which are complex numbers. The wave function is in complex numbers. But square of the wave function probabilities, that alpha square and beta square, are probabilities which are real, not complex. So I want everyone to think, why should complex variables come into the linear superposition? That is an important question. In linear algebra and other phenomena in classical physics, we don't encounter, it is possible, but we don't encounter linear superposition using complex quantities. But this is very important for us now. In this quantum information technology, it is very important to understand why the linear superposition can involve complex numbers. That means it is throwing out many possibilities, not only 45 degrees, etc. So you can also think in terms of the amplitude and phase. But we must recall that it is only a probability. The wave function has got a certain electric field with a probability. So we can also put this in the superposition in the polar coordinates. You also see on the left hand side the blot sphere. So what is done here is simply a square. This equation you can put it in the geometric form: alpha into 0 ket plus beta into 1 ket. You can assume x and y for the variables, and alpha and beta for the coefficients, and psi for the output. If you do, then you get a sphere. Okay, you can think of a projection also. If you want to get less confusion, you can say you will do the 2D plane, and you will have a circle. So all the points on the sphere or circle are the possible values for the wave function, or possible values for the qubit state. Now let us move to multiple qubits. I hope everyone has got the point. Maybe we'll have discussion towards the end if you are confused. So we are not going to deal with only one qubit. So we want to, you see, there is another important point. I suppose you must have already come across in this FDP itself. See, we should also look at what is meant by information. See, because we have said quantum information technology, we should also consider what is information. I think most of you must have already thought about that. As you know, information is defined in terms of certain possibilities. Suppose you have a coin tossing experiment. Head has got certain possibility and tail has got certain possibility, and you define the amount of information in the coin tossing experiment. You know, one bit of information is there in a coin tossing experiment because there are two events and each are equally possible. You have one bit of information. You can extend easily. Suppose you have a dice instead of coin. So the amount of information contained in throwing of a dice is also related to probability. Is it not? So 1/6 possibility. So you can calculate. And many of you know that we have to calculate the entropy of the information system. See, suppose you have symbols S1, S2, S3 up to Sn with their corresponding possibilities P1, P2, P3 up to Pn. Then you know the entropy of the system, which represents the expected value of this probability distribution, is given by pi log pi, sum of all those things. I hope you can recall all those. I am assuming that someone else would have talked about all this. I can focus more on the implementation and photonics related issues. If you are still confused, you may please ask me again later on. So when we move to multiple qubits, what happens? You must have two photons. Each one, all the properties that we have mentioned earlier. The state of the first photon is not known, state of the second photon is not known. Each is represented by their wave function psi1 and psi2, and you have a joint probability distribution function for the two photon system or two qubit system. So you have all these four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1 ket. and these are nothing but averages of the joint probability distribution functions. I am assuming non-correlation and all those properties. For the simplicity, let us assume they are not related. So psi is a linear combination of 0, 0 ket, 0, 1 ket, 1, 0 ket, and 1, 1 ket with alpha 1, alpha 2, alpha 3, alpha 4 as the coefficients can be complex with the same arguments that we have given earlier. That means for a 2-qubit system, we have 4 basis functions. It's a linear combination of 4 basic vectors. So now you can imagine what happens if you talk about n-qubit system. You have psi as a linear combination of 2 power n basis vectors. So it is scaling very enormously. Number of possibilities, number of points that are possible, etc., is going exponentially. That is the reason we say that. See, of course, there is a good theoretical proofs. We can say that a n qubit computer can do the work of a 2 power n bit classical system. So let us get going. Quantum gates. We'll quickly extend. We'll use, see, I would like to mention that all these things can be translated into matrix form. You can say 0, 0 ket as the vector. You can represent it by column vector 0, 0, 0, 1, 1. Then 0, 1 as 0, 0, 1, 0. 1, 0 as 0, 1, 0, 0. And this is one of the basis vectors. There are a lot of all possibilities. There are many, as you know, in linear algebra, you can have many basis vectors. There is also a unique basis vector that you can create by using orthonormality and all that. Okay, I will assume that way. So that the input-output relationships gates are one form of the input-output relationships. So I am just describing a few gates which are somewhat unique to quantum computing. For example, polygate is a single qubit gate. And input-output relationship is represented by this matrix 0, 1, 1, 0. That means I am assuming the input qubit state as 0, 1, for example, and the output qubit state as y or some other variable. Then multiplying this 0, 1, 1, 0 matrix with the input, you get the output. Similarly, there is what is called this poly y gate, poly z gate. Now you can work out that linear position superposition. What does it come out? So suppose, for example, if you look at X gate, you say if you are given 0 qubit, then you get 1 qubit at the output. That means it is doing the NOT operation. Similarly, see the poly Y gate is translating the input qubit state into some combination of that, including one of them to be the imaginary numbers. Another example I have is the Hadamard gate, represented by this matrix, 1, 1, 1 minus 1. So you can see that the input qubit state is transformed into linear combination of 0 ket and 1 ket. So this is a very strange thing which doesn't exist in the classical domain. You can also imagine this as rotation by 45 degrees or minus 45 degrees. So input qubit state, if it is a horizontally polarized photon, the output is a 45 degrees rotated photon. So you can also think of, there are, I think you must have already seen this, C0 gate consists of 2 input qubits and 2 output qubits, and this is the matrix. You can the 4 by 4 matrix you have for, because C can take 2 values, T can take 2 values, so you have various combinations 0, 0, 0, 1, 1, 0, 0, 0, etc. So C is representing the control qubit state and T is representing the signal qubit state. If you look from the matrix, if you see the first 4 elements 1, 0, 0, 1 for the C, that means it's an identity matrix. That means if C is 0 qubit state, then output is not changed. Whereas if C is 0, 1, 1, 0, the last 4 digits, then it is performing as a NOT gate. So C is controlling the what happens to the qubit state T. So it is a controlled NOT, you can say. Similarly, you can think of double C NOT. There are 2 control qubit states and 1 signal qubit input, and you can also work out all the matrix. So you will get an 8 by 8 matrix in which you have first four elements belonging to C1, identity matrix, next one to C2, and so on and so forth. So you have all the analogs of classical gates. Whatever are there in classical domain, you can easily represent it in the quantum domain. So these are all what is called Divincenzo criteria. See, if you want to build a quantum computer or quantum information system, we demand a lot of conditions. For example, the first one says we must be able to scale the system. Suppose I build a quantum computer with 8 qubits. Then we should be able to, with the same idea, we should be able to scale it to some 16 qubits or 64 qubits. That's what is meant by scaling. It's not easy sometimes. It's become, depending on the physical situation, it's not so easy to scale. See, for example, if I'm talking about a photonic states, we have to generate so many photons. You have to control so many photons. Okay, so that's what is the challenge in this each of these criteria for that matter. So we should also be able to initialize the qubit states before starting the program or so. Like in the classical computers, you know that you will initialize the registers in a classical computer. Similarly, we should be able to initialize the states of the qubit. There's another important issue with respect to all these quantum states. So they are not stable enough. They will be stable only for a certain period of time. This property of the qubit states is called the decoherence. That means the state of the qubit changes after a certain time. Similarly, one more criteria people are trying to work out is there any universal set of quantum gates which can build quantum computers? Like we are familiar with NAND gates. In CMOS circuits, we know NAND gates can perform a lot of things. You can boil down all the logic operations to NAND operations. Similarly, is there any universal set of quantum gates? For example, C naught. Maybe it may be possible to define C naught as a universal quantum gate. Some of the implementations do that. Then there's another important property of the quantum systems. We are not able to measure what is the photon state. Suppose I say photon is in the 45 degrees state. Then it is only with a probability. So when you measure, you get the photon with only a probability. We cannot divide that, is it not? We cannot split the photon. So measurement is an important capability. We have to work out various means in which to guess or to deduce what is the state of the photon or qubit. So similarly, there are a lot of such criteria, many criteria people try to come up with. Each one of them is a very serious, important point which requires treatment and careful thinking before we build the quantum information systems. So this is a brief block diagram of a quantum computer. How does a quantum computer look like? One of the basic ideas in quantum, such as systems, or in many of the engineering systems, is to take a phased approach. You can divide the design of a quantum computer into many, many layers. Like you recall, we have the OSI protocol. Suppose you want to build the internet. Suppose you want to transfer files from one computer to another computer or on the internet. We use 7-layer model, starting with the physical layer, the data link layer, network layer, and so on up to application layer. Similarly, people try to design quantum computers by using layered approach. So this is a very brief block diagram showing how it is done. Not all layers are shown here. See, they start with a mathematical model. See, this is a computational approach. See, what is your computing problem that you're trying to solve? Whether trying to solve some, say, for example, a database problem or image processing problem. So based on the algorithm, you should start with a mathematical model. We should reduce the function in terms of mathematics, a sequence of mathematical operations. Then you should translate them into computational formulation. See, mathematical formulation need not be fully computational because we have to reduce it. So all computations are not possible in a straightforward way. So in classical computing as well as quantum computing, there will be different formulations. That's what is meant by the second block. We must translate into a computational formulation. Then you should reduce to compilation. You must group all these operations together to compile the sequence of operations. Based on that, you develop a software. You can call it as a quantum software. See, if you look at how the present day computing and internet operations are taking place, it's a very complicated thing. Even a simple thing like a cell phone, what we are using, if you talk on a cell phone to someone else abroad, there are a lot of a sequence of operations and protocols that are going on there. So we should imagine all those things when you are talking about a quantum computer also. Of course, finally, we should translate them into physical system. What are the devices which will implement this? Is an important question. That's where the bottleneck in quantum computing is there presently. So we should reduce all these quantum algorithms and all these blocks that we have talked about until now onto physical systems, starting with the laser diodes, photodetectors, then photonic devices, and so on. And so I'll show you a few devices as we go along. So below this is shown in terms of notation. So I will ignore that for the time being. The reference is given here for those who are interested. So this is almost the same thing that I have mentioned here. But one important point I would like to mention here is there are a lot of quantum simulators nowadays. You can, all the algorithms, quantum algorithms that you have reduced can be put in some simulator, a sequence of steps, which you may run on a classical computer also, what they call semi-classical or semi-quantum implementation you can do. So that's what is done when IBM gives you some working space for doing the quantum. It gives all the good interface. It represents all the quantum functionalities, etc., that you have. But the actual computing inside is somewhat semi-classical, you can say. Like what you please recall what phenomena has mentioned. We should catch hold of a quantum phenomena like photoelectric effect. See, photoelectric is a real quantum phenomena. So the output of that is represented by some mathematics, which is the real quantum computing. Okay, I hope you have reflected on that point during this time. Now let us get into one example of a quantum communication. You can say that quantum communication exploits the quantum nature of objects to represent information, and you will require all these. I'm now coming down to the device level, not in the block diagram. You require a source of quantum information. You require a very high speed photo detector. You must study the properties of the channel that you are using, like the free space or an optical fiber or whatever it is. And you have to consider the noise involved in the system, like conventional noises. You also have the quantum noise. You have noise due to the detector, various types of disturbances. In fact, the errors in the computation itself, when you translate an algorithm into computational form, there are errors. So those also can be considered as a noise. Similarly, in many systems, security is an important thing. There are eavesdroppers trying to steal the information. You have to take care of all these things. And in the quantum domain. So channels I have put in the end. There are a lot of channels available nowadays. Most common, you can say a fiber optic link can be used as a quantum channel, because fiber optic links are there all over India, all over the world. You can use the conventional cable systems, whatever you have, but you modulate the laser diode and all the terminal equipment you can replace with quantum um, hardware, you can say. Similarly, another important example I have put here is the gravitational waves. As you know, the universe, if you look at the universe as a whole, there's a lot of quantum phenomena happening. For example, the nuclear reactions in the sun are really quantum phenomena. Then gravitational waves. If there are two extraterrestrial objects like a black holes, they are interacting by gravitational waves. They are getting attracted, and so on and so forth. So gravitational waves are there connecting all these extraterrestrial objects. And people have already found out that gravitation is also quantized. You have um, quantum gravity, or the gravitational waves are also quantized, like electromagnetic waves and light waves. So please think over that. It's a very interesting subject. So entanglement, I just like to mention, it may be needed in many algorithms. We need to have what is kind of called a quantum entanglement. Quantum entanglement implies that the two objects are correlated. Properties of 1 and 2, I'm showing them as coin tossing experiments, are related. Suppose you know the properties of one coin tossing experiment, you will know the quantum tossing experiment of the other one also. So you have a subset of all these possible states I have put here. Right, for the time being, I will not use this. I will only show you one example of this protocol, how it is done. I don't know whether someone has already done that. So this is the BB84 protocol. The Alice is trying to transmit quantum information to Bob. It can be classical information also, but let us assume this bulb is representing the qubit states, and you have two different ways to transmit. See, Alice has got the option to choose horizontal and vertical polarization, or right circularly polarized and left circularly polarized. Two different ways. See, you recall the basis linear superposition that we have seen earlier. There are different possibilities for the basis states. So horizontal vertical is one possibility, and minus right circularly polarized and left circularly polarized waves is another possibility. The crux of the algorithm, this BB84 protocol, is Alice will choose these bases in a random way. So first qubit, she may choose the first one. Second qubit, she may choose the second one. Third qubit, she may choose to represent using once again the second um, polarization state, and so on and so forth. So that is done it randomly. That is the importance. That is the key point in the BB84 protocol. Now at the Bob's end also, he will also have an option to choose the basis randomly to detect the incoming qubit. So he can use horizontal vertical or LC RC. And these Bob and Alice act independently. And then they will compare in the end. You see, first of all, before all the communication starts, they will make a lookup table of what Alice sent, which polarization and so on, and then try to match which are the possible combinations that they should use. So now let us make a table, lookup table of the bit sequence, and then the photon sequence of the Alice, then the detected base sequence, and the result, and the compatibility. So Alice is one is the first qubit state. Alice is using plus 45 degrees polarized light to transmit, and Bob is using the vertically polarized vertical horizontal state basis to recognize that it is 0. So it's not compatible because the recognition is not correct. Similarly, second one, if you take one qubit state with vertical horizon polarization, vertical horizon polarization detection, and so it's a compatible thing. So there are all these possible combinations are there, 16 possible combinations. So you see that 50% of the combinations are not compatible. So that means in this BB84 protocol, compatibility is 50%. So they can discard, they can use only the lookup table consisting of all the compatibility states, compatibility combinations. So that is the importance of the BB84 protocol. Now, how does the security come into picture? Suppose Eve is trying to steal the information in between. What she will do this, she knows that these people are using the BB84 protocol, using horizontal, vertical, and plus 45, minus 45, and she will get 4 machines, detect and transmit randomly, once again, like what Alice and Bob are doing. Then from outside, we need to make a table like this, which will contain 32 combinations. Out of that, how many combinations are compatible? Once Alice and Bob compare with their lookup table, they will see only 25% of the combinations are compatible. That means they will immediately know that something wrong has happened, some compromise has happened, and someone is interpreting. So this just shows how quantum communication can take place for secure communication. So there are a lot of new protocols now. BB84 itself has been modified, E91, E92, etc. So many protocols have come. A lot of new techniques are there, depending on the technology also. So instead of using bulk polarizers, etc., you can use polarizers on the integrated platforms and so on. So I'll show you a few block diagrams of recent developments in quantum communications. So this is the first one, Mesius 1 satellite by Chinese. They have transmitted several kilowatts of power from ground to the satellite, and from satellite to the ground station in Austria, and so on. So I hope people have thought about that. They are transmitting large number of photons, not single photon. See, suppose you want to transmit light from ground station to satellite, you need to pump in several kilowatts or watts of power. So how do you embed this quantum information in these qubits, in these pulses is an important question you should think of. So there's also, they're not communicating only between 2 points, but there are several users. So how do you communicate? What are the algorithms? How do you calculate the probabilities, that compatibility table, and so on and so forth? So recently people have started working on this and trying to develop and protocols that can, broadly speaking, we can say that the probabilities are distributed. So probabilities are distributed across different users. For example, if there is a user A communicating with B and C, suppose A wants to transmit to both, communicate with both B and C. It is not possible to send photon to both of them. Unlike in classical system, you can broadcast. You can send the same information to B as well as C, and then B and C will recognize their own information. By using the header information, they can take whatever information they have. This is not possible here like this because the photon cannot be divided. A can transmit only to B or C with some probability. So you have to work out, look at all the possible combinations, and then you have to work out how this quantum internet works. So now let us look at a few methods of implementing quantum technology using photonics. So I would like to mention that there are different platforms are available at this moment. As you know, silicon is the most common platform because of VLSI. See, most of our CMOS circuits, VLSI is based on silicon. So people have started using integrated photonics on silicon. But as you know, you cannot make lasers, photodetectors easily on silicon. You need active materials like indium phosphide and so on, 3-5 compound semiconductors. But people have been using crystals like lithium niobate, lithium tantalate, KTP, and so on and so forth for realizing photonic applications. So we should look. You see, this is an important problem. That's how, for the future of quantum technology, the hardware or the technological part, technological advances are important. So let us go further. I'll show you a few pictures of implementation of quantum technology using integrated photonics. So integrated quantum devices for communications. Say first, let us look at classical applications. Then we'll go to quantum applications. I'll switch to another set of slides. So I'll show you a little bit about photonics, integrated photonics. So that, of course, in future, those who are more interested can go deeper into the subject and implementation issues. And if you want to take up some projects, etc., this information may be useful. So, as I said earlier, let me start with integrated photonics. Aims to create various optical components on a single substrate. For a few slides, you ignore quantum. We'll come back to the quantum later on. So integrated photonics aims to create various optical components in a small substrate, like in VLSI. Of course, at this moment, we are a very, very primitive stage, you can say. This is also analogous to integrated electronics. Electronics also has developed ICs. Similarly, optical ICs. So a lot of examples are already there in the literature and in practice. So there are N by N switch arrays. If you want to set up an optical network, you can switch between different users directly without getting to optical domain by using switch arrays. Similarly, since this is a sensor application, fiber optic gyroscope is a sensor for rotation, for the measurement of rotation of an object, like an aircraft or missile. If it is rotating, you can use a fiber optic gyroscope to sense it. It's a very, very sensitive sensor. Similarly, there's another idea more than 20 years ago now already. People have developed what is called an optical bench on a chip. On a silicon wafer, you can create mirrors, then moving elements, actuators, and so on, so that you can align. Like in an optical table, you can have a silicon optical table. This is called a micro optical bench. So this combines mechanical elements, optical elements, and some control elements also on the chip. So I'll show you one or two examples just for your. I hope many of you would not have encountered integrated photonics, so it may be interesting to you. This is an example of a high-speed optical modulator. Want to modulate a light wave at some several gigabits per second, how do you do is an important question. Here, what you are seeing is the top view of a what is called an interferometer, mag center interferometer. You have a Y branch which can divide the power between two arms of this interferometer. These blue patches are um, electrodes. You can put your RF signal onto that control signal, and then it basically will phase modulate. See, the waveguide propagation can also be described in terms of e power I beta z. That means if the refractive index of the waveguide changes, then it is phase modulated. So this combiner will translate that into intensity modulation. So if you want to do a high speed modulation, this is a very good way. You are not changing the properties of the laser diode. Okay, so that's an important problem in high speed modulation. If you directly modulate the laser diode, then it can become unstable and you may not have a perfect modulation. So this is called an external modulator, very common, commercially also available for optical communication applications. So another important device is called the optical switch. There are two waveguides very close together. There are two inputs in input ports, S1 and S2, which can be switched by applying voltages across these electrodes. S1 and S2 can become S2 and S1, the signals. So you can exchange signal between two users by using this. It's a very it's not a very common thing. If you go mathematically, you can easily understand, but light propagating in the first waveguide can exchange into the second waveguide to create this crossover state. And it can go back. If you double the length or if you double the refractive index, then S1 and S2 can become S1 and S2 back. So you can get the crossover state or bar state by switching these electrode voltages. These are all the technological parameters that I've shown here. So that's all as an example. There are a lot of examples are there. I can give you if you want. I would like to show you a few optical devices like waveguides, branches, modulators, switches. So maybe in future, if necessary, if someone wants to learn more, we can have a technical talk on these photonic integrated circuits. So I would like to show these are passive devices. See Y branch. If you want to divide the power between two output arms, you can use a Y branch. You can divide it across three output ports. You can cascade 2 by 2, 1 by 2 branches to make 1 by 4 power dividers. It's not easy to divide power, is it not? You know that light propagates in straight lines. In a waveguide, if light is propagating, it's very difficult to distract or deviate it from the straight path. Suppose you want to make a 90 degrees bend. It's not very straightforward thing. A lot of power can lose. You have to design that curvature properly and all that. So I'll show you some application. Polarizers. You have to control the polarization of light in propagating in optical circuits. So then you can use these waveguide polarizers. Similarly, you can create multiplexers, demultiplexers. If you want, if many channels are coming from an optical fiber, you can demultiplex them into different channels, lambda 1, lambda 2, etc. So each channel is characterized by different wavelength. You can make lenses on this chip. You can make gratings. Gratings are multi-purpose usage, like input-output coupling you can do from fiber to the chip and from chip to the fiber. Then you can also control the modes. As you know, all these waveguides, etc., have modes of propagation, not simply uniform plane waves. So they are defined in terms of the modes. So in our research also, I'll show you in one slide how we are using the modes to represent quantum information. And they are used in lasers for as a mirrors or a reflectors. Laser cavities you can create by using gratings. These are all the applications of gratings. So I think that's all about the photonics. We'll go back to so these are fiber optic communication system 4x4 switch array. This is the optical information processing system. You can analyze the full entire spectrum of RF signal using such a photonic IC. Similarly, this is the fiber optic gyroscope I was talking about. This is a coil you have here. You have the light going in the clockwise direction and anti-clockwise direction. When they superpose at this point, the phase difference between them will give you the rotation rate. Delta phi is proportional to omega. So for this, we have to make this chip. So you have to use a laser diode, photodetector, you have to use a single mode waveguides, you have to use a couplers, there's a phase modulator, there's a combiner, polarizer, all these things are needed for a fiber optic gyroscope. In earlier days, people used to do all this on the discrete components separately using fibers and using control electronics and so on. So in our lab, we have worked on this fiber optic gyroscope chip. So you can make all these things on a small lithium niobate substrate. Long ago, when I was a student, one of the engineers from RCI Hyderabad was working on this fiber optic gyroscope chip. These are all some new developments which we'll ignore for the time being. We'll go back to our quantum. So I'll show you some pictures of integrated quantum communication devices. So all this, I'm giving you the papers from where I have taken all this, so you can go to them for more details. This is an example of an integrated quantum communication device. So it is mainly for generation and manipulation of qubit states. Examples of integrated device for generation and manipulation of quantum photonic states. You can observe that there is a grating coupler. That's why I have shown you earlier all those integrated photonic devices. Then you have a ring resonator. See, a ring resonator is nothing but a waveguide formed in the form of ring, and it can resonate. Light can go round and round. It can get coupled from this bus waveguide to the ring and then coupled, and you can create these two states, blue state and red state I'm showing you. It can be horizontal polarization and vertical polarization. And then this grating can be designed such that it can reflect one state and transmit one state. It can deflect in two different directions also. So I'm using a combination of ring resonators to separate out the signal and this idler, what you call, two different. You see, what usually done is signal power is less. So you can use the support of an idler to manipulate the properties of the signal. So you can, for example, you can tune the second um, ring resonator for the idler state and the first one for the signal state. Both can be qubit states and so on. This is an example of a generation. This is a complete circuit containing integrated communication devices. You can see the similar things that I have shown earlier. So this is a chip for generation of manipulation of qubits or the single qubit states. You have a multi-layer combination consisting of electrode on one end. You have the substrate. You have the active layer where the quantum phenomena take place. That is a quantum well. And the mirrors are created by using gratings. And you have an electrodes on the other side also. On ground electrode, on electrode, you can manipulate the generation of these photons. So I'll go to one more example. So these are complete chip that someone has developed for detection of photons. So people have also developed quantum key distribution systems. You can make everything on. Of course, this is only a block diagram here, not a circuit, a real circuit. So you can make all the necessary components for a quantum key distribution on a small wafer. One more, next one also I'll show you. So these are photonic chip architecture, which consists of all the. It is maybe based on the silicon. It has got a phase modulator. You have got a shallow, deep etched circuit waveguide device, and an amplifier also is built in the same chip. So I will show you a few slides from the work that we have done in our lab, and then we can conclude. So in our lab, we have worked on quantum cryptography. Then a few quantum algorithms were tried to see how they can be implemented using photonic circuits and so on. One example I'll show you. So this is an example of another recent work is based on the higher dimensional quantum key distribution. Instead of using only zero state in one state, we can use intermediate states. Like for example, if you look at a photon, then there are other possibilities like 45 degrees, 60 degrees, and so on. So we can have a multi-level, multi-qubit state. So this is called qubits. Instead of having qubits, you have qubits instead of D1, D2, D3, D4. So it will greatly enhance. You can recall that we said 2 power n is the order of scaling. So this will have a d power n scaling. So this is an example, recent example that we have done. We have used an optical circuit to represent this Hadamard gate. Instead of using horizontal and vertical polarization, we have used TE mode and TM mode. For those who are familiar with electromagnetics and wave theory, you know that light confinement is defined in terms of the TETM modes. I'm showing you T0 mode as representing the 0 ket and TM1 representing the 1 qubit state. So if you look at the functionality of the Y branch, you will observe that, see, a linear combination of this T0 and T1 state is what is coming out. That means 0 ket plus 1 ket. So you can observe that this is the Hadamard operation that we defined earlier. But of course, there are a lot of interesting phenomena in this for those who want to work out mathematically and to understand. For example, the propagation constants of T0 and T1 are different, not like horizontal and vertical polarization. Then the boundary conditions are there. And then a lot of strange phenomena that will happen at the junctions. There is also a taper here. Waveguide width is becoming from W to 2W. Suppose you call W as the width of the waveguide, it becomes 2W. So the mode is getting transformed. These are all the things that we need to study if you want to work out on this. Then in other of our studies, we have used what are called photonic crystals. These are like metamaterials, periodic structures, which can be used to manipulate light propagation characteristics and all that. So we have also worked out on implementing QKD using these photonic circuits and worked out what is the efficiency that is possible and all that in one of our papers. So the other faculty in our department, he is working on generating single photon sources. That's an important requirement in quantum computing and communications. So we can generate single photon sources by using by propagating the light in ring resonators coupled to bus waveguides and so on. So that's all I think I'll have to mention right now. This is our group, and we have a lot of activity, a lot of educational activity, a lot of people are doing projects, and also a few those who are interested. We have internships. There's a big group in IAC working on quantum information technology. There are about 3 faculty also on different aspects of quantum, like quantum sources, sensing, measurements. Our lab works on photonic devices and so on. I'll show you 1 or 2 slides about the thesis that we have done by our students. So this is one of our earlier thesis, first thesis, you can say. He had worked on algorithmic aspects using photonic circuits. Then I would like to show you another one. Akshita has worked on quantum cryptography, random number generation, quantum information processing, and all these things. You can see our papers which are listed here. So we had also worked on machine learning combined with photonics. So Bhavani has worked on evaluating the page rank using a quantum simulator. Similarly, he has developed or he has proposed a deep neural network in photonics domain. You can use, see, I have shown you earlier optical switches. You can cascade optical switches to create larger and larger photonic networks. That's all I have for the time being. Thank you very much for listening. We'll have some discussion if someone is interested. Yes, please. The organizers can coordinate if someone is interested to ask questions.
Professor, this is Mahesh Rao from Kinfosys Private Limited, Hyderabad.
Yes.
Professor, I see first time, in fact, I was not familiar about you.
Yes.
I could see you today in your talk that you are very much fascinated in photonic technology. And
Yes.
thanks for very insightful talk. Professor, just I have one query. I would like to meet you sometimes actually.
Yeah, you
After
are
this,
welcome to ISC. We have a big
we are
quantum center.
establishing quantum photonic laboratory in Hyderabad in our company.
Okay.
And
Yeah.
I want to meet you. It's a great opportunity to meet you today here. And
Yes.
definitely I will contact you sooner or later.
Yeah, definitely.
One question I want to ask you related to this talk that
Yes.
you have taken that the Uh, Rather than taking basic states in two-dimensional, you have taken in higher dimensional, right? So,
Yes,
and you have taken, definitely it provides a better security. I do agree.
yes,
What about
yes.
performance aspects?
Fabrication. Huh?
No, what about in terms of performance?
Oh, performance. See, in
Yeah.
one of our papers, we have evaluated how this BB84 protocol works for higher dimensional.
Oh,
Uh, you see, instead of using D1, D2, D3, etc., we have shown that it is much more efficient than conventional work.
really? Oh,
It's not
interesting.
exactly scaling exponentially,
Uh-huh.
but much better than the conventional.
So,
We expect d power n times, but it's
mhm,
not exactly so. There are a lot of other intricate things when we want work. But one nice thing about that is, I
mhm,
want to mention
mhm,
implementation issue. For
mhm,
example, if you want to implement using optical circuits,
mhm,
is not at all very complicated. It is only scaling very simply. For example, I can make a four mode waveguide. I'm showing you here two mode waveguide, T0 and T1 only. I can easily design these waveguide circuits for higher dimensions. It's very easy to make four mode wave. For example, doubling the width will make four mode waveguide. So like that, we can work out all the directional couplers and all the photonic circuits that I've shown. We can easily convert them into higher dimensions.
so higher dimension, you mean usually we take in Hilbert space. Do you
Yes.
take in something in quaternion space or something? Or
No,
again,
no, it's not exactly quaternions,
uh,
but n-dimensional vector space, you can say.
oh,
Suppose n qubits if you have,
mm.
n qubit states, n qubit states if you have, then it's a space in the n dimensions
So
instead of
same,
having two dimensions or three dimensions.
same Hilbert space you are dividing.
Yes, yes,
Okay.
C power n, what you call Hilbert space in Cn.
CN. Okay.
Earlier we have only C square or and so on.
Okay.
But mathematics is somewhat available, not necessarily for these applications,
Mm.
but all the Hilbert space and vector spaces um, is available in many dimensions also right now,
Yeah.
but they may not be applied until now. I don't know. We have to work out which are applicable to quantum domain, various results of Hilbert
So
spaces.
is there any correlation between photonic behavior and higher dimension, any size of dimension that under our experimental results?
Yeah,
Or
yeah, it
just
is very easy. It appears. You see, right now, until now, we have done much of it is analytical, except for some small circuits like this. But you see, if you look at bulk optics, for example, the polarization, you can use polarizers and polarization controllers to prepare qubits in any input states. For example, 45 degrees, we can
mm,
easily create.
yeah.
See, suppose you send the photon through a 45 degrees polarizer. You
Mm,
say that it is starting point is 45 degrees.
mm.
So it is in optical domain, it is very easy. You may already recall if you are using superconducting qubits or atomic systems, it's very, very difficult to control and manipulate. Whereas in optical domain, it appears to be somewhat easy.
So do you mean that eavesdropper can easily manipulate?
See, that is already there, always there, but it gets more and more tougher for eavesdropper. See, for example, if I use 4 qubit QKD,
Mm,
4 qubit QKD, then
mm,
Alice has got four systems,
mm,
then Bob has got four systems,
mm,
and then Eve has to get eight systems
mm,
to manipulate. And then the probability,
mm.
the that lookup table or compatibility table is very small. So the probability, the security becomes much more higher if you use qubit states.
Yeah, obviously, because you are increasing the dimension and
Yes.
more permutations, more
Yes,
combination.
more possibilities. Yes, more combinations.
Yeah. Thank you, Professor.
Yeah, I am aware about like developments in India and also particularly in Bangalore. I know some of these companies like
Professor, thank
who are
you.
working on these
Thank,
subjects. Of course,
after
Hyderabad also. I know. I see. We have what I maybe for information for everyone. We have what is called this Photonic Society.
okay.
Many of our people are members of IEEE Photonic Society. That's where all this information is published and authentic information. I would like to mention all the participants that if you want to get the latest information about photonics and in particular for quantum, I suppose many of you have realized that this is very indispensable for quantum technology. See, we don't have the quantum computers proper what is that called? Practical quantum computers, mainly because of the technological problem. And photonics seems to be a very good solution. So if you are interested in the subject, you please look at the papers, journals from IEEE Photonics Society. Of
Yeah.
course, communications, IEEE has got many societies. I suppose many of you know. There's a communication society, there is a computer society, and so on and so forth. But photonics is very indispensable. If someone is interested, um, we can form in your college, or see, we are trying to. I was talking to Dr. Vijaya also that we can form a photonic society chapter of the Vijayawada region. As you know, now after the bifurcation of the state, the Hyderabad section has got a photonics chapter, but in Vizag and Vijayawada region and Tirupati region, there's not much activity. There's no society, first of all. There is IEEE activities there, but not much on the photonics. So if someone is interested, we can help you to do that. We have also a national group of photonics professionals. There are about 35 photonics society chapters in India in different colleges. So if you are interested, we can have a short discussion later on some other time on this photonics. It's very simple. You can just go to the IEEE website and look at what is this photonics society and what are the subjects of interest. Not only quantum, they deal with nonlinear optics, lasers, biomedical applications, and so on. If you are interested in any aspect of photonics, you can join this photonics society. And
Professor,
I will offer for today, I will offer for one or two faculty from Vijaya College. If you are already a member of Photonic Society, or if you joined just now, we can offer you an ex-com position.
Thank you, sir.
Welcome.
Thank you very much. We
Professor,
have
one more
3 to
question.
4 IEEE members, sir. We are also going to start the IEEE chapter,
Yes.
but we need to include this photonics also in that. Students also interested, sir. So
Yeah.
nearly 10 to
See,
12 members are
recently
there.
when I came to SRM in
Ah,
Vijayawada, I talked to some of my students are there. I asked them to help you to form the Photonics chapter.
yes, sir. Yes, sir. I will take help from them, sir.
Yeah, we need only, see, first of all, you have to have your student branch active.
Yes, sir.
Then
Yes,
we'll
sir.
think of Photonics chapters. Okay.
By the next month, we will start, sir. It is already in the process, sir.
Yeah, in Bangalore, we have a lot of activity. We have summer
Mm.
school on photonics.
Yes,
Every
sir.
year we
That
conduct.
Srinivasan sir also, we contacted him, and he also interested to guide us, sir.
Yeah, he did PhD in our lab on photonic
Yes,
band gap
sir.
structures.
Yes, sir.
Professor, one more question, Professor.
Yes, please.
Uh, Actually, after this talk, I will also write to you to get your appointment.
Yes.
I will be visiting Bangalore
Yeah.
sometime.
Yeah.
Definitely, I will meet you face to face.
Yes, please.
So, is there for sensing technology, is
Yes.
photonics something is contributing for sensing, or is
Yeah,
that?
yeah. See, I have given one example in my deviation slides. We have what is called this fiber optic gyroscope. See, RCA Hyderabad has developed this fiber optic gyroscope that is now used in all our systems. In defense systems, they are using it.
Sensing.
So that is a very important sensor. Earlier, they were importing, and now we are able to make it in India. And a lot of sensors now. See, we have MEMS activities there in India already, everywhere in DRDO labs and everywhere. So you can do a lot of sensors. For example, in our lab, we have done MEMS-based sub-micronewton force sensor. You can detect fractions of newtons. So a lot of sensing applications. In fact, photonics actually, originally, if you look at measurement and sensing, optical techniques have been very, very sensitive compared to all other technologies. So photonics has an important role to play in sensing.
Okay.
And also biosensing. We must also, related to sensing is biosensing. A lot of biomedical parameters can be easily sensed by using optical circuits. In particular, I would like to mention that we need to go for integrated because we want to have very small circuits, very functional, very efficient, and so on and so forth.
No. Professor, I am particularly asking, is photonic technology is contributing for any sensing, or only you are talking about microelectronics mechanical system?
No. You see, this is called MOEMs, micro opto electromechanical systems, in which most important application is to sensors, physical sensors, chemical sensors, biosensors. All sorts of sensors are people have made on using optical techniques, photonics.
Okay, right.
That's a very important hot subject. If you look at IEEE journals or Photonics Society website, in fact, there are also a couple of conferences. Every year they have a conference on optical MEMS and optical circuits and so on. See, one of the important things that our people have to do is to get into real international conferences. See, most of these, for example, if you go to right now, for example, this week, there is a Photonics Global Conference going on in China. That's where a lot of recent developments in the photonics take place. Mm. So we should be aware, and it is costly affair because it's very difficult to go abroad for conferences from India, and also a lot of other difficulties like registration fees is high and so on. But it's absolutely needed for us to track what is happening globally.
Exactly.
Excuse me, sir.
Yes.
Sir, I have one question.
Yes, please.
So regarding quantum computer, we are always
Yes.
aware of that environmental condition.
Yes.
For this, when we inculcate that in fiber optics, is it clear while transmitting the information through this fiber optic cable? That
Yes.
transmission of qubit
There
information.
are two parts that you are asking. One is about the system, quantum
Yes.
computing system. So, see, if you look at the existing quantum computers, like from IBM and all these other places, they are very big. Most of them, many of them, the major technology right now is superconducting qubits. That means the states are at very low temperature. That's why you see such big ones. They require a lot of cooling, control, and all that. Then in the near future, people will go for electronic systems. In the CMOS circuits itself, you can find out some states which can be used as a qubit states. Then our existing VLSI technology can be used directly for that. Then in the long run, we have to use optical techniques. The whole of this lecture we are emphasizing on using the photons instead of electrons. So these will be at room temperature. We don't need to have cooling and all these things, control. And it will be very simple, like electronic circuits. Like for example, the cell phone, we are not using it at a low temperature.
Yes.
We are using it room temperature. Similarly, quantum functions can be implemented at a room temperature and well packaged and all that. So that is the near future. The next question that you have asked is about the communication part.
Yes, sir. Yes, sir. That
If
is,
you want to
how
transmit
the
qubit
error rate
information
will
in photonics,
control.
fiber optics is the very good technique because fiber optics is there everywhere, all over the country. You have fiber optic cables. So only thermal equipment, if you properly launching of qubits, modulation, and so on, if you control, you can use the existing fiber optic links for quantum communications.
Okay. Thank you, sir.
Yes.
Participants, if you have any queries, the forum is open for you. Please raise your queries. Sir, I think no more queries.
Sir, I have one more question, sir.
Yes, please.
Sir, here, how the time interval will control, sir, while transmitting the information.
Yes.
But here, nowadays, the research is on depending upon the time interval while transfer of message from one point to another point. So in this particular technology
Yes.
also, we have to control the time easily.
Yes. Let me make one comment. See, presently, the method of our detection, method of our modulation, etc., is based on your time interval. See, we divide the time into several slots, and in each slot, you put a pulse. In electronics, you cannot go beyond a certain time interval. Say, for example, a few terahertz rates is possible. Whereas in optics, you can go for much lower. Femtosecond rates, you can easily go because you can generate ultra short pulses. Ultra short pulses are very, very small, femtosecond. That means you can go for smaller and smaller intervals. That is one approach using the what is called your time intervals.
Okay,
So
sir.
you can go for much smaller, much higher data rates. See, why
Hmm.
are we able to go for several Gbps in a fiber optic cable? Gbps is still in microwave domain only if you translate into gigabits per second or gigahertz.
So
Femtosecond is still smaller. Terabits per second is
yes, sir.
possible.
While concentrating on video transmission, it is very curious to maintain that particular time intervals. That's why I'm asking.
Yes.
Hmm.
Yeah, if you are using the current digital technology, you
Ah.
have this difficulty of
Hmm.
digitizing, quantizing, and all that.
Yes, sir.
But what people are trying to do in photonics is you use a what is called a functional approach.
Okay.
Suppose you want to do image processing, you want to you take the Fourier transform of an object. What do you do? In electronics, you divide it into all the pixels, use Cooley-Tukey algorithm or signal processing techniques, and then finally you get the Fourier transform of that object. Whereas in optics, what people do, you put the object in front of a lens. You take a thin lens, then at the other focal plane of the lens, you get the Fourier transform of the object, all points on the object parallelly transformed onto the image plane.
Okay.
Is only the distance is only the limitation. See, suppose you have a few centimeters or a few millimeters as the distance between the object and the image plane. That is the time it takes for transformation. It's very, very faster than any electronic system.
Yes.
So these are called the functional approaches. So instead of creating digital logic in quantum or photonics, we can simply create optical elements like lenses, then these waveguides, then all these circuits, whatever I have been, photonic bandgap structures, ring resonators. These will do very, very functional um, approach towards all the things that we are talking about.
Okay, sir. Thank you,
Of course,
sir.
there is also digital photonics. People talk about replacing with quantum gates, photonic gates, and so on. Yes, I think if anyone has doubts, you can please send me. You can collect their questions and then you can send me on the email. I can respond also. And if someone is interested in any other aspect, whichever we know, you can see our website, and I can we can discuss online also. If someone is coming to Bangalore, you can see IAC. We have a nano center which can fabricate all these things. In our lab, we mainly actually I forgot to mention we are mainly experimental people. But a lot of theory also we have been doing because of requirement for the publications for our theses, our students, etc. We have developed a lot of theory also. But our main interest is in experiments. We can make all these Y branches, photonic bandgap structures, ring resonators, all these optical devices, simple optical devices, not very complicated ones. We can fabricate in IAC. Yeah, actually, it is a national center. Anyone can come and work in that nano center. You can please see the website of our nano center. Center for Nanoscience in Engineering, it is called.
Okay, sir. Thank you so much, sir, for your
Yeah.
cooperation in this regard. And I would like to give a quick whatever you have to say.
नहीं जैसा काम पे जा रहे हैं
So, in this today's session by Dr. Srinivas Talabatla, sir explained us clearly, very quickly regarding what are all the topics that we have gone through, like quantum computer and communication history of quantum computer, and the differences between classical and quantum computing, and why the reason we call quantum computing as there is quantum supremacy, and the timeline of quantum computing with milestones and its applications that we have seen clearly, and qubit, what is the called or basic bit of quantum data, and what are all the quantum gates, and how these are formed, how these are analyzed, and the scaling of quantum gates, block diagram of quantum computing, and the scientific and classical information or classical data difference between general and quantum data, and the information regarding, particularly till today we have seen what is quantum and quantum computing, but sir named the itself, or the session itself, very cleverly, namely quantum information, so that we have had a new idea on what is actually happening in quantum computing in sir's point of view very clearly. So once again, thank you so much, sir, for all your grateful inputs in this short span of time, and for your hope for us to contribute your knowledge in our future endeavors also. Sir. Thank you so much, sir, for being with us today with your valuable time spending with us. Sir.
Thank you very much once again.
Thank you, sir.
Thank you.
Now we will move to the next session. Today here with us again, sir, from Quenfosys, Dr. Maheshwar Rao sir Valluri. Sir has already taken up a session with us on day 2, the session number 4 on the hands-on training regarding nanoscale devices and CMOS applications. Sir, Dr. Valluri sir, I with warm heart welcome you to take over the session again today on this FDP of Day-4. Sir.
Hello.
Yes.
Good evening, one and all. Today, my session on quantum search algorithms and applications. I have taken this topic because Madam Dr. Vijay asked to provide some hands-on. I use 3 devices today to explain these concepts. Even I use digital board. I also use some programming. We run this search algorithm on Google Circ. Okay, let us start with search algorithms. We do have 2 types of data searches. One is structured data search, another one is unstructured data, right? In structured data, we can do search very fast on a classical computer, which takes order log n. Same structured data we can do on quantum computer, order square root n. So what is the best for sorted database? Still classical is search is better than quantum search. So this is an example that quantum alone can't provide in all the cases that better uh, search. So in sorted database, classical system performs better than quantum. So it's not the case that always quantum provides better search than quantum. In indexed data, indexing reduces search space, quantum search applies with the sections. In a graphical structured data, quantum walk for graph search, which takes order square root n. And in 2-dimensional lattices, it takes order n log n. So quantum search can complement classical methods, especially in hybrid models. For unstructured data, one of the famous algorithms is Grover's algorithm, which can provide better search than any of the classical. Classical problem, given an uncertain database of n, marking the one of the elements in the database, we need order n classical queries. Whereas in quantum system, we need order square root n. So what does it mean? Suppose if you search in Google database, and if you want to find a particular term on Google search, so if you attempt on classical 100 times, but same task you can do in 10 times. The reason square root of 100. So which takes quadratic speed up from amplitude amplification. So it's a more technical aspect. We'll discuss how does it do. So what is a quantum oracle? I use whiteboard sometimes. The oracle itself is a black box which can identify. For example, if I ask a question, what's your name? You'll be able to tell your name that you are a particular person. If I ask a discrete question, decision making question, suppose you are Srinivas. Are you Srinivas? You may say your response is yes, I'm a Srinivas. But do you know that how your brain has been processed to say your answer Srinivas? You don't know it, right? But you are able to say your response yes. So our brain itself is a black box. So oracle, we do have two types of oracles. One is classical one oracle, another one is quantum oracle. In our scenario, we use quantum oracle. The oracle in quantum search algorithms mask the target state, and which is essential for Grover's algorithm. How do you define the oracle function? I use whiteboard to and switch sometimes to explain these concepts. So stop sharing here. I'll share in another device to explain a little bit about oracles. It's a quantum oracle. Quantum oracle. Actually, we define like this. We have two wires, say two registers. First register X, second register Y. So two registers, this is the oracle function YF. And in this, it provides output X, whereas in this, it provides Y F of X, where F of X equals to, or F we define as a function from n-bit string to discrete decision set 0, 1. Suppose if you ask question this oracle or black box, any question you raise from this input, it can provide response here. Response in the sense of either yes, no. So this we define using this small circuit. It's called oracle circuit for quantum. So in the first register, you can keep the X. This is the input. Second register, you can keep Y, and you can ask, it can provide ket X as output, same in the first wire. Second wire, Y XOR F of X. We can slightly alter this circuit. In the input, first input we provide here, ket X. And in second register, we use ket 0. Then if you ask this function, OF, oracle function, so in the first wire, it remains same, whereas in second wire, we have 0 XOR F of X. So what does it mean? F of X. This is the target. This is the target. So what you can understand here, if you want to evaluate any of the functions, functional values, you can use simply a oracle function. It can provide a response in terms of discrete values, right? So you'll be able to find the functional value by using this oracle function. This oracle function is a foundational stuff for many of the quantum algorithms. So this is called bit flipping oracle. We do have similarly phase oracle. In phase oracle, we take input X and it applies phase operator. It provides minus of X ket X, the functional value here, sorry. So it depends on the function. Suppose f of X equals to, in the database we have, database D, say, for example, 0 to 1, 2, 3, and so on, we have 100 people up to 99. Our target X star equals to, suppose, 50. So how do you define this function? F of X equals to target. We reached 1. if x star equals to 50. Then we can define this 0 if x not equals to x star, right? We can define this function. So you can see this, how this function behaves because of Oracle. If you provide, suppose you put 0, this Oracle provides functional value as an output minus 1 power f of x value for x equals to 0, 0. So it provides output 0. It provides positive value. Likewise, if you take 1, it provides y of Oracle function minus 1 power. Functional value 0 for all, it provides same, right? So likewise, you can do for all. If you take the functional value, for example, if you take 50 as input, Oracle function y of here, it will generate minus 1 power. If f of x value, if it is x star, that is target equals to 50, we do get 1, right? 1 get 50. So we can see that minus 50. So this is how we can identify phase happens in a phase shift happens in the phase Oracle function. That's all we can target in the crowd. If we take the 50 people in this 99 people, suppose we have 99 people, some amplitude times get 0, some amplitude times get 1, some amplitude times get 2, and so on. We can write like this. This is the wave function. We are keeping these all people in superposition. Only in the case of 50, the amplitude is negative. Rest cases, positive. The amplitude is here, positive. In all the cases, amplitude is positive. So this is how we can use this Oracle function and phase Oracle to identify the target with a different sign, rather than keeping for all the other cases positive sign, whereas for target element is negative sign. So we can identify the person in the crowd and we can pull him. So that's how we can do such technique. This is the one of the stuff that is contributing for fastest calculation in Grover's algorithm. Well, let me go back to again the world system, the other slides. Yeah. So what I have done here, the Oracle function in such algorithms marks the target state and is essential for Grover's algorithm. Oracle definition, unitary operation, U acts. Oracle on ket x provides minus ket x. If I not equals to x, it provides positive. Flips the phase of the target state, leaves others unchanged. Oracle in Grover's algorithm applied repeatedly to amplify the target state's amplitude. So we can represent this Oracle in terms of matrices. Oracle O equals to I identity matrix minus 2 times of kx bra x. It is called outer product. So this is how Oracle contributes for identifying the target in a crowd. So how Grover's algorithm works? Grover's algorithm starts with the preparing the quantum state in initialization position. If you don't mind, shall I use whiteboard so that easy to explain by taking an example? Everybody can easily understand. Then I can explain these slides so that it is easy. Okay? Is it fine, madam?
Sir.
Hello?
Hi, sir. It is clear, sir.
Okay. So I use whiteboard to explain Grover's algorithm, then I use hands-on, then I can use slides so that easy to explain rest of the stuff, how we can apply this Grover's algorithm in real-time scenarios case. Okay. So let us discuss Grover's algorithm for small database here. Let us take database D equals to, we take uncertain data, you can put them, small size we take so that easy to do computation, toy model. We have cat 0, cat 1, cat 2, and cat 3, which we can write in terms of binary data, cat 0, 0, cat 0, 1, cat 1, 0, cat 1, 1, right? Do you agree with me? Right? So this is the data. So how many qubits we used here? N equals to 2 power n. So number of qubits equals to 2 qubits we used here. 2 qubits and 4 classical bits. 4 classical bits we used here. 4 classical bits we used. Right? How do you generate these classical bits corresponding to these qubits 0, 0? Qubit 0, 0 we can write in terms of vector. We use ket 0, tensor product ket 0. Actually, ket 0, 0, we can represent in 4 dimensions, but 1 qubit we represent in 2 dimensions, 2 qubits we represent in 4 dimensions. So ket 0 we can take as 1, 0, tensor product 0. If you do this, we get 1, 0, 0, 0. Likewise, for other qubits, 0, 1, if you do tensor product, get 0, tensor product, get 1. So 0, 1, 0, 0, you can obtain. Likewise, get 1, 0, you can get 1, tensor product, get 0, you can obtain in this scenario, 0, 0, 1, 0. Get 1, 1 case, you can obtain get 1, tensor product, get 1. Here, you can obtain 0, 0, 0, 1. Right. So this is the basic information which we need. First, in step 1, what we do, we need to initialize the state. So we have 0, tensor product 2 qubits. And when we take, we can apply Hadamard gate. Hadamard gate 2 times. We know Hadamard gate H equals to 1 by square root 2 tensor product. Sorry. H equals to 1 by square root 2 1, 1, 1, minus 1. This is the Hadamard gate. What Hadamard gate can do, if we take Hadamard gate on qubit 0, it can take into superposition 1 by square root 2, get 0 plus get 1. We can write in terms of vectors 1, 1. Likewise, if we take Hadamard gate on qubit 1, it can provide output 1 by square root 2, get 0 minus get 1, where we can write in terms of vectors 1 minus 1. Right. So if we apply Hadamard gate on 2 qubits, we are applying 2 times. We are getting 1 by square root 2, get 0 plus get 1. Tensor product 1 by square root 2, get 0 plus get 1. We can put it this way. Then when you multiply these two, 1 by 2 square root 2 times 1 by square root 2, 1 by 2. We can multiply the corresponding qubits. Get 0 tensor product get 0. Get 0 tensor product get 1. Get 1 tensor product get 0. Get 1 tensor product get 1. So we can write in simplified manner this one 1 by 2 get 0 0 get 0 1 plus get 1 0 get 1 1. So we can represent in terms of vectors 1 by 2 1 0 0 0. So in simple language we can write 1 by 2 1, 1, 1, 1. Right? So this is the state. After applying head-made gate on qubit 0, that is a ground state. That is one of the criteria that we need to keep the quantum machine in always in ground state. If you apply head-made gate 2 times, you are getting superposition. This is the state to represent superposition. This is in terms of classical representation, but generally we use superposition, right? So this position is called superposition, right? After applying head-made gate, we obtain this state, right? Now what we do, let us look at this way. There are 4 people. We want to identify one of the person. Which person do you want to identify? Let us assume we don't know, but our target is one of the persons. Let us say 3. 3 is our target. We consider X star, right? Our target is X star. So let us define the Oracle function. We define the Oracle function F, which we map from, in our case, 0, 1, right? We define. If we take qubit 0, 0, if you apply Oracle function, right? If you apply Oracle function, here f of x value 0 if x equals to x naught equals to x star, and 1 if x equals to x star. We define the Oracle function. So in our case, our target is 3, right? Ket 3. So in our Ket 3 case, is our target? No, right? Minus 1 power, functional value here, 0. So it remains Ket 0, 0. In the case of Ket 0, 1, if you apply again Oracle function, minus 1 power 0, functional value 0, 1. So here 1, 0, functional value UF, minus 1 power 0, 1, 0. Again, if you take 1, 1, the functional value minus 1 power 1, 1, 1. So what we can see here, Ket 0, 0, Ket 0, 1, Ket 1, 0, Ket minus Ket 1, 1. So if you apply this Oracle function, step 2, Oracle on Ket Zyna, that is initialization, then you are obtaining UF on Ket Zyna, you are obtaining another state. This is the, after applying, we are obtaining Ket Zy1 state in the machine. So what you get in this 1 by 2, 1 by 2, right? Ket 0, 0 remains same. Ket 0, 1, 0, 1. Ket 1, 0, same. Ket 1, 1 case, minus sign. Isn't it? Because of after applying only for the target, because our target is x star equals to 3, where f of x value 1. For rest all the cases, f of x value 0. Right? We already identified the person target in the crowd. But how do you pull him from the database? It's a crowd, right? It's a database. But we identified in the database. But how do you pull him out? So for pulling out, Grover applied diffusion operator. That's diffusion operator. Step 3, diffusion Grover's operator or diffusion operator. So diffusion operator D equals to 2 times of get J naught, bra J naught on initialization condition minus I. This is called Grover's operator. We know that this we can put it as a in terms of vectors, 2 times of get J naught value. What is the get J naught value in terms of vector? 1 by 2, 1, 1, 1. Right. What about this? Bra value, again 1 by 2. Bra is nothing but in terms of again rows. minus I. Now we put it 2 by 4. We are getting 1, 1, 1, 1. Is it 1, 1, 1, 1, 1, 1, 1, 1? A square matrix. Sorry. Minus identity matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Right. So we can write this 1 by 2, 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 1. If you apply minus 1, 0, 0, 0, what are you going to apply get here? Only for this first diagonal element negative sign, rest cases positives. Right? Is it? Now we already calculated Grover's operator. We need to, in step 4, again, if you apply Grover's operator on, after applying on ket xi1, apply D on ket xi1. That is after applying Oracle function. So you are going to get again another state, the one of the states, that is the next level. Ket xi2, let us consider D over ket xi1. So we know this D is in terms of matrices minus 1 by 2, 1 by 2, 1 by 2, 1 by 2, 1 by 2 minus 1 by 2, 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 minus 1 by 2, 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 minus 1 by 2. So this ket xi1 you can write in terms of matrix. Again, we can write 1 by 2. This you can write 1, 0, 0, 0, 0, 1, 0, 0. You can write 0, 0, 1, 0. You can write last 0, 0, 0, 1. So you can present this as 1 by 2, 1, 1, 1, minus 1. Right? So then you can put that 1 by 2, 1, 1, 1, minus 1. Now you can do multiplication, right? So, or you can put it directly. This 1 by 2, 1 by 2, 1 by 2, minus 1 by 2. Remove this. Now we can multiply. Minus 1 by 4, plus 1 by 4, plus 1 by 4, minus 1 by 4. If we multiply, first row, 1 by 4, minus 1 by 4, plus 1 by 4, minus 1 by 4. Second case. Third case, 1 by 4, 1 by 4, minus 1 by 4, minus 1 by 4. Fourth case, 1 by 4, 1 by 4, 1 by 4, minus 1 by, minus of minus plus 1 by 4. So you are going to see this 0, 0, 0, 1. This is equals to 1, 1. This is the target. You are going to get the extracting the target. This is how we can extract this target. Okay, so we got right. So this is equivalent to this. This is how Grover's algorithm works. This is our toy model, which I explained using the white digital board. Any doubt here you can raise, then we can also, I can also show you that how we can apply on Google Search language. Can I go for that? Just give me 1 more minute. I'll show you this. To save time, I have written the code. I will explain you. Yeah. I switch into again my another PC. Yeah. So this is just Google it. You can go to Google Colab. Right. This is a Google Colab. Where you can install Circ language. Okay. From this, I pull the, yeah, okay. I'm copying the code, pre-written code. Okay. I'll explain this code. Just I run this code, we see. Yeah. Actually, this is the output. We use number of sorts, 1000. This is the circuit for growers. We have taken small data size, that is only 4 qubits. I mean 2 qubits, 4 classical bits data. So this is how we can generalize this, and which we are running on using Google's simulator. You can see that simulate the circuit simulator we use, circ.simulator. So let me explain this. After slides explaining, I want to explain this code now. Okay? Or do you want to explain the first code? So let me explain this. We have to import a circ package, and which is from again Python NumPy. So we define the qubits here. We take 2 qubits. So circ dot, we do have line qubits, grid qubits, and named qubits. We can define in 3 aspects, the qubits. Then we defined here Oracle function. We can define Oracle function different approach, what are the way. Then we also, like it's similar to writing Python code, and we also defined diffusion operator here. So we define diffusion operator. In order to define the diffusion operator, we need to carefully choose the gates that we need to produce the required output. And after that, what we have used, we build the grower circuit. And in the circuit, we have to follow the procedure that how we initialize the system. After initializing, For initialization into superposition, we applied Hedemade gate. Here we applied on each wire Hedemade gates. Then we applied Oracle, phase Oracle. Then we applied diffusion operator. Then finally, we measured the system circuit. Each wire we measured. So apart from that, we also used backend simulator, circ simulator, it's a Google simulator. We obtained results, and we also asked to repeat how many times you want. You can put it 1,000 times, 10 times. It depends how many times you want. Then obviously you want to see the output. And you want to see the output, you can see circuit, you can call the circuit, and also see in terms of histogram, and also see in terms of results. Now I change the number of shots. You can see this. The shots have been reduced. Yeah, only 10 shots were used. This is the output. This is the circuit. This is the histogram for this. This is just a toy model. Right? Any questions you can ask now. Now I explain the concept. Right. This gentleman is the Grover. In Grover's algorithm, we claim that Grover's algorithm provides better search than classical system. In a classical system, we require for data size of n, order n classical queries. I mean queries, complexity of the query, order n. Whereas in Grover's system on quantum, we require only order square root n. Right. So how Grover algorithm works, let us discuss. First, what we need to do, we need to keep the machine in the ground state, that is zero state or initialization state. If you apply Hedemade gate to all the qubits, it can take the system into superposition. We have data size n. By applying Hedemade gate for all these, we could get the superposition state. This state is the superposition state. In superposition state, we need to observe that amplitude is equally distributed. That is, in this scenario, 1 by square root order n. If you expand this sigma function, we can obtain I equals to 0 to n minus 1. How I expanded like 1 by square root 2 power n, 2 power 2 square. That means 1 by square root 4 in our example, 1 by 2. Then we expand 0 to n minus 1. Our case, classical data, n equals to 4. So get 0 plus get 1 plus get 2 plus get 3, we expanded like that. So where n is the total number of possible state, get I is the basis state. After applying initialization state, what we have done, we applied the Oracle function to mark the target. Let us consider our target. Actually, data we represented in this as I. Target we are representing it as a X. In our example, I put it X and X star, right? The Oracle flips the phase of the target. If the target is X, then it provides output negative sign. For rest of the cases, positive sign. We have in database n items. Out of n items, our target is to find one item. So that item is X. So our targeted item is X. When you apply Oracle function on targeted item, we obtain negative sign for the targeted items. For rest all the cases, positive sign. So it leaves all the states unchanged. The Oracle is critical for identifying the correct state during the search process. That's what we have done, targeting. So the same, in terms of matrices, we can represent. The Oracle operator can be represented as matrix, or you can put it as a direct notation, Oracle function O, I times I minus 2 times of outer product, Ktex, X, where I is the identity matrix, Ktex is the target state. We have to take as a target state. This operator efficiently flips the phase of the target state and leaves rest. We applied a diffusion operator. After marking the target state, the diffusion operator amplifies the probability of the mark state, which we put it d equals to 2 times of get xi naught bra xi naught minus I. We applied already this. This operator inverts about the mean. It increases the amplitude of the marked state, which helps in finding the correct state here. After that, what we have done, we need to apply, because we have taken small database, we could identify in a single step. But each iteration of the Grover's algorithm involves applying the oracle to the market state, applying the diffusion operator to amplify the market state probability. The total which we can obtain, that is Grover's number of Grover's operators that we apply, that's where the complexity is involved. That's why we have taken complexity under square root n. G equals to D for diffusion operator, O for oracle. Right. So we need to analyze in terms of geometry. Actually, we have done in terms of just logical aspects. In geometrical aspects, the amplitude of the target state, evolves into each iteration. After k iterations, the probability of finding the target state can be obtained, because we are taking this entire system in the Hilbert space of n dimension, and we can represent in terms of sine and cos functions, and we can put it that in angle. Amplitude means actually change of angle, right? Change of position. And after k iteration, we'll be able to obtain. So to obtaining, we need maximum number of iterations, k star. After order n iterations, we'll be able to find the exact solution. That's where the success comes. This is where the complexity involves. Grover's algorithm can be visualized as a rotation in two-dimensional subspace that we put it the target and untarget. Right? So we can put it the ket 0 as x, ket 1 as x, what I call inverse process or flip process. Each iteration applies a rotation in this 2D. Angular rotation, we can put it, and finally k, after k rotations, we'll be able to obtain the position. So we have limitations. Success probability high, but not exact in Grover's. We have to do here in this process this many rotations. Sine square 2k plus 1 plus theta. Non-optical k leads to lower success probability, which requires knowledge of the number of marked state. The total complexity is a significant contributor to the total cost here. So that's just a quantum approach, Grover's algorithm. If we go for hybrid approach, classical and quantum search, because we need to have optimizations, we are using optimized methods. Classical pre-processing reduces search domain. We know that if you go for data, so we can do first step, sorted, unsorted. Unsorted data, we know that quantum is better, whereas sorted data, classical is better. But we don't know which one we are going to use, because in database is there, which one is sorted data, which one is unsorted data. For sorted data, if you use classical system, which requires, as I mentioned, that order log n, where is enough. So classical system is better than quantum in classical sorted data, whereas in unsorted data, quantum is the beta. So we need to go for optimality when you make it any system for searching. Another search algorithm is quantum walk. Quantum walk search, which we put it as a unitary operator, u, which we can put it as a function, 2 times pi. This function is defined as a walking function. Sigma v belongs to v, ket v outer product, tensor product, ket xi v, tensor product, bra xi v, where S is the shift operator on hedges. So if you mark on some graphs, we use mostly in a graph theory, order n greater enough, whereas in two-dimensional lattice, order n log n enough. Quantum walks outperform Grovers when structure is present. And also we do use continuous variable quantum search. Continuous variant of Grover's acts on Hilbert space of dimension 2. We can also use not only discrete system, we can also use continuous system, where we can use the target region A, which belongs to some space, which is a real domain. We can define that ket xi equals to, in terms of wave function, integral xi naught of x ket x dx. And also we can define Varakil function, x minus sign for the target, positive sign for non-target. So in that speed up, classical system 1 by p, quantum system order 1 by square root p, where p is the probability that happens to get the target x. This is another model, because we can use either Grover's method, depends on the model of the computation that you are using. Suppose if you are using superconducting system, mostly we use a qubit system, discrete system, where you can use Grover's algorithm. Suppose if you are using continuous variable quantum search system, like a D-wave computer or photonic system, where we use variational quantum computation, in that kind of scenarios, we can implement this. Applications, database search. Quantum search algorithms provide a significant speed up for searching uncertain database. Uncertain database search, finding a marked element in uncertain database, which requires complexity order n, whereas in quantum system order square root n. So which can provide quadratic speed up. So these kind of applications we can use in finding the customer ID, documentation, or any large data like a Google and all. We can also implement this search algorithms in quantum machine learning, where we can see that optimality of the search. Quantum search plays a key role in enhancing machine learning tasks by optimizing search operations. Mostly we apply it in a feature selection. Quantum search can efficiently identify relevant features in large database. And also we can use nearest neighbor search techniques. Quantum search can speed up in finding nearest neighbor search in data set. So where we can apply Grover's algorithm. And also in quantum nearest neighbor search, the search complexities also we can apply, where we can see that Grover's is always better performance, better than the classical search algorithm. And this Grover's algorithm we can also apply in crypto analysis. Quantum search can improve efficiency in attacking mostly in a symmetric crypto system, where we can apply brute force attack. We do have a lot of security algorithms. Mostly, suppose we have ATM card. In ATM pin, we do have number of possibilities. If you look at the keyboard size 0 to 9, we can apply 0 to 9, 10 digits. And we can also have password length 4 bits, 4 digits. So if you apply permutations and combination techniques, we can have 10 power 4. 10 power 4 equals to 10,000, right? 10,000 attempts we can do, but we according to bank policy, only 3 attempts can be allowed, right? If we apply Grover's algorithm to attack password, so order square root 10,000, order square root 10,000, which is equivalent to 100. 100 attempts enough. In a classical system, if you want to attempt password, we need to attempt 1,000 times, 10,000 times. Whereas in quantum system, using Grovers, we can apply brute force attack. Within 100 attempts, we can be able to find the password of the ATM card. So that's how we can apply brute force attack. So breaking cryptographic systems, searching through large key space, we can efficiently break. For example, you take AES algorithm, advanced encryption algorithm that we use, where the key size is 128 keys, 128 bits, right? So we can attempt brute force attack by, as of today, on a classical system, if you choose 89 bits, right? So we are using minimal size for AES 128. If you apply Grover's algorithm, we can be able to break in order 2 power 64 queries. That means there is a huge threat to existing AES encryption algorithm. So once quantum is available, we need to increase the key search. So we need to develop to provide same level of security where we have 128 bit key size to be 256 bits key we need to use so that it can provide same level of security. So this is how it impacts security system. And next one is we can also use Grover's algorithm in combinatorial optimizations. Quantum search is also useful in solving combinatorial optimization problems efficiently. So mostly in travel salesman problem and optimizations and snapshot problems and generalized search space. In these are all scenarios we can apply Grover's algorithm. In the most of the cases, same number of queries we need to ask. Order square root n. Another one is mostly this important application that we discuss most of the time in many places, drug discovery. One of the key applications of quantum is drug discovery because to identify molecules and molecule structures, protein folds and all, years, scientists are spending time for identifying the medicine. If you apply quantum machine learning models, and we can easily identify behavior and pattern of drug, I mean, bacteria and virus and protein, easily identify the pattern and find the medicine or find the drug. So this is a significant application once quantum is accessible to everyone. So most of the biological scientists spend time to use the quantum machine learning models to find the drugs. So in that process also, we need to have optimization system for searching. Any search that we use quantum models, we have to use, as of today, the best standard model is a Grover search algorithm. So if you apply Grover search algorithm, always the case, if you have data size of n, which is able to provide in a order square root n. So quadratic speed up, whereas in classical system, it takes order n attempts. That's the advantage. In the Grover's algorithm, we can also apply Grover's algorithm in drug discovery. Another application, significant application is supply chain optimizations. Similar situation. We can apply Grover's algorithm in supply chain, in which we apply in routing problems, inventory management systems, and also optimal supply chain configuration systems. We can use Grover's search algorithm. And also we can apply in a image and text retrieval process, image retrieval, text retrieval, and a natural language process. Wherever we use the machine learning models or searching and optimization, we can use these Grovers. It can provide advantage than the classical system. And also in a graph theory and network, in graph search, social network, quantum walks, graph search, and all, we can apply this grovers which can provide quadratic speed up. And also we can use this network security where we can naturally use the quantum machine learning models for detecting intruders and also recognizing the pattern. So we can apply, and also we can find the vulnerability scanning system. We can apply Grover's algorithm, which can provide a fast search. And similarly, we can also use this Grover's algorithm, automated theory, and also logical search, where we use automated proof search, constraint satisfaction problems, logical inference, logical search complexity, and many other scenarios. These are the things where we can apply the search algorithm. The significant search algorithm is the Grover's algorithm. And the second one is a quantum walk. It doesn't provide much significant, but we can use quantum walk for multi-dimensional system like a GPS system, because we don't go directly from linearly. Grid system we use. In grid system, we can use quantum walk. And in variational system, like mostly in quantum machine learning or quantum AI applications, suppose if you want to recognize anything on the surface of the earth, so if you go with the discrete structure, you will not be able to find. And if you go with the continuous variable system, you'll be able to find easily, in which we can also apply this search technique. Mostly in defensive. Suppose you are using like drones. Suppose drone is used somewhere the targeted items on the earth. So how do you find it? So you need to use search technique. You need to apply sensing system. From there you will be able to find it from very sensitive area. If you want to identify such systems, if you apply the continuous variables quantum search algorithms, you will be able to find easily. So these are all just generalization from Grover's algorithm. Grover's is the best for discrete structure, whereas same Grover's can be applied in many scenarios, not only for discrete, but also for variational. Right? It's a more technical aspects. If you have any questions, I'm ready to answer.
Thank you, sir, for your session. Requesting the participants to raise their voice if they have any queries. Please move forward.
Members, are you familiar with the Grover's algorithm? Most of you, I believe you are familiar. This is one of the algorithms only, a famous algorithm. Hello?
Sir,
Is it? Hello?
sir, I have one question. For every algorithm, every search algorithm, Hadamard plays a main role.
Yes, because you want to take it to superposition.
Yes, sir. So that entanglement and superposition will give good response. Other than that, is there any, sir?
Okay, actually in quantum, three phenomena. One is superposition. In superposition, I give best example. We are 79 people, 78 people right now.
Mm.
Physically sitting 78 people, let us assume in a hall, theater, physically sitting. You are there in one of the chairs, right?
Mm.
I use my eye contact. I use my eye contact to identify you, search you, right? So
Mm.
if I want to find you, I need to use my eyeballs for at least 78 times, right? I need to check everyone, right?
Mm. Yes, sir.
But if I take this into superposition by applying head-made gate, I can see you all at a time. I don't require to rotate my eyeballs. I can
Mm.
see you all the 78 people at a time. Is it not the best feature in quantum?
Yes, sir.
That's one of. I give
Mm.
another scenario, best example to explain that. Generally, Professor Srinivas spoken about photonic.
Yes, sir.
Uh, when we switch on, uh, we have electrical bulb. When you switch on, what is happening there? Electrons transferred into photons,
Mm.
right? Bulb filament on. When bulb filament on, what happens? The entire room gives brightness.
Mm.
Is it not the superposition?
Yes, sir.
Is it not the yes? Is it not the superposition? Because the electrical switch power on, as soon as you switch on the power, bulb filament on, the filament itself is providing brightness in entire room. That's the photonic behavior. That's the superposition, right? So
Yes, sir.
that is one of the features contributing for fast computation. Second scenario, entanglement. Entanglement is a mystery in quantum mechanics because two particles, suppose even I described in my last session, universally it is acceptable, and uh, I don't know whether I should take it or not. Two souls connected once, and irrespective of the distance, both the souls think about one another and influence one another. It is there in human behavior. That's called people call love, the
Mm.
soul connection. One person thinks, same thing, another person thinks. They both are interact irrespective of the distance because same level of energy. And a similar behavior there in quantum. So what we say that quantum particles also can fall in love, which is a mystery, and it is there in the nature. Albert Einstein proposed this in 1929, EPR pair. And later, I think in 1980s, experimentally done this work. And in 2022, Nobel Prize was given for this experimental work for quantum entanglement. And the third one is quantum interference. We could see, the professor also explained just before. When we represent even superposition, I also put it. I have taken how many qubits I have taken? 2 qubits I have taken. When I have taken 2 qubits, when I applied head-made gate, those 2 qubits, how many states we expanded? Ket 0, 0, ket 0, 1, ket 1, 1, 1, 0, ket 1, 1, right? There are 4 states, right? I mean, four-dimensional. Four-dimensional. Have you noticed four-dimensional, right? Yes or no?
Yes, sir.
But when it comes to quantum entanglement, what happened? Ket 0, 0 plus ket 1, 1.
Mm.
Remaining ket 0 and ket 1 amplitude disappeared.
Mm.
So interference happened. Again, sometimes later, those again appearing. How is it possible? That's called quantum interference. I put it this another way. You take it to two stones, and those 2 stones at a time put in water. When I put in the water these 2 stones, we are going to see the waves, right? Waves coming. Those two waves coming, after coming one another, they are they are interfering, right? Hitting one another. What is happening after that in water? Going. I'm taking one hand, one stone, another hand, another stone. I'm putting both the stones at a time in water, steady water. When I put those two stones in the steady water, right side, left side going wave well, very safely. And after sometimes those two waves fade out. But what happens? Both are coming same side, one another hitting, right? After hitting, what happens? Those waves, do they go back? Do they collide? That itself is a quantum interference. So the third one is no cloning theorem. No cloning theorem is the best way to describe about quantum, just a coin tossing. When you take the coin, rotate the coin on the table. When I rotate the coin on the table, after energy drops out, it can provide output either head or tail, right? So that we can represent ket 0 or ket 1. But if you stop that using your fingers, then we know the state, but it's not fallen down. It's there in standing position, but not rotating. That itself is an Adamant gate, a superposition. But during spinning, we don't know state, right? That state will not be able to copy because we don't know the state. We don't know how to find it. Using that state, we communicate. Quantum teleportation is implemented for unknown state. You are able to send through classical fiber network unknown quantum bits through classical internet from one end to another end so that it can communicate. This the protocol is called quantum teleportation. And the same thing, same methodology is used even in KKD protocol. So these are the things are contributing for secure communication. No cloning theorem is the key, which is providing security. Right, madam?
Okay, sir.
Yeah.
And one more doubt, sir.
It's more like technical. So I can see that today is very dry. I'm also very sick.
Yes, sir. No, sir, it's clear, but it is nothing but a searching algorithm, sir.
Only one searching algorithm.
Only one searching algorithm. But my doubt is when we transmit the information in terms of bits.
Hmm.
I'm completely on communication system side, sir. That's why I'm asking. While transferring the information,
Oh.
here we are using so many types of encoding and decoding techniques at the transmitter side and the receiver side.
Hmm. Hmm. Yeah,
At that time, I already asked Srinivas sir also that doubt while in photonics transmission also,
yeah.
but here also I have that encoding decoding side also. There is a full-fledged transmission will happen or not? Is there any error will occur while transmitting that qubits?
Yeah, yeah. First thing you are talking about encoding the classical information to quantum or after.
Quantum, sir. Quantum. Suppose if I have some information, sir, at the input, I am converting it into qubits, and then I'm such out of all those bits, I am going to transmit only some of the bits by using this searching algorithm, and then I have to write certain encoding technique, and then transmission of that information.
Yeah, okay. That you
Hmm.
can do that. That you can do that using teleportation or super dense coding.
Okay.
So transmitting data is possible, but here there is no transmission in this model. Only the data is there. See, like how I can say that it's mostly this search algorithm used in database. Already data there, like
Yes, sir. Data is there.
list
From that
data.
data, we have to select what are the basic things we need to train.
Suppose in the country, Aadhaar card,
Hmm.
we listed number of citizens, their database, their ID, this zigzag, lot of used data, right?
Mm.
Suppose take India. So in India, we have server and we have millions of the people, and we want to identify particularly your ID, your Aadhaar card number.
Mm.
So if mission takes a lot of time, you get frustrated. If you implement Grover's algorithm, and it can quickly identify, right? In a
Yes, sir.
So that kind of application, this one, because nothing to do with that anything. For example, password, your password, right?
Mm.
So your password is from any password from any keyboard, right? In our computer keyboard, we have 256 keys, right?
Mm.
We have 256 keys. And then your password length is only five characters. So then if you identify 256 power 5, you can definitely find that many permutations possible, permutations and combinations. If you apply Grover's, you will be able to square root of that. I mean, 256 power 5 square root value steps enough to find the password. So we can do faster. What I mean to say here,
Mm.
the brute force is possible. For example, password, ATM password. ATM password, we have 10 key. I mean, 0 to 9 we use. Password length, four digits, right? So we can calculate this way, 10 power 4. 10 power 4 equals to 10,000, right? So if you want to find pin of your ATM, if you attempt in worst case on classical system, 10,000 times, definitely we can find your password. But if you apply for the same scenario, this Grover's quantum algorithm, square root of 10,000 times. Square root of 10,000 times which value? Just 100, right? Am I correct? 100 square value, 10,000. Square root of 10,000 equals to 100. Classical system, 10,000 times required, whereas on quantum system, just 100 attempts enough to find your password. So what do you see that? Quantum is contributing for faster search. So what we need to do? We need to increase your key size, password size, so that you will not have quantum threat. To increase your key size, again, we have problem with the infrastructure.
Mm.
Right? In classical system, if you want to use, again, you're doubling up your password, right? Password length. When you double up your password length, key space is increasing, the data size is increasing. And when you increase the data size, again, what is the problem? Searching time is more.
Mm.
So then it's all complexity is increasing, system is becoming slow. These are the parameters in terms of computing. I'm not talking in terms of communication.
Yes, sir.
So,
No, actually, my problem is I have set of videos, sir. Out of all that videos, I have to select what is the required thing related to that particular video. There are so many activities in that video. I have to select one particular activity out of all those. For that, I am using that Grover search algorithm. After that, I want to encode all the data. So
hmm.
across that particular condition, is there any hybrid model for searching and for encoding? Like that, that question, that doubt I
So
have, sir.
this can only provide for searching, not
Yeah,
for
only
so. But
searching.
you are applying again features. Actually,
Mm,
you want to find particular image or video, so that can be detected by machine learning.
mm.
So you need to use quantum machine learning and Grover's algorithm for optimization of search. And
Only again, same learning methods and again training, and
yes.
everything will be coming into DL.
Yes,
Mm,
exactly. See, we are detecting, optimizing, searching. Three
mm.
activities you need. For detections, you have to use, if it is physical system, sensing system, right? Searching,
That's
it is growers. And recognizing pattern, you need to use machine learning.
machine.
So if you apply these three technologies, you will be able to handle the project well with the
Yes.
optimality. Yeah.
Thank you, sir.
Sorry, I am sick today. However, I thought to contribute.
No problem, sir.
Yeah. Any other questions? This is too technical. Hope you could understand, but you need to have prerequisite knowledge. Even I feel dry to explain this. The reason for that, I don't know whether you have background knowledge. If you have background knowledge, easy to explain. But when I'm taking here and jumping directly, and it is providing a challenge. Yeah. Any other questions? No. Hello? Hello?
Thank you so much for your patiently explaining all the queries of our four candidates and our HOD ma'am. I would like to just give the brief and today's session of your topic, sir. So in this session from Dr. Mahesh Sir already we have seen how search efficiency can be increased drastically using structured algorithms in quantum computing. What is in a detailed step-by-step manner we have seen. And sir has also explained the Grover's algorithm and its various application areas with regard to theoretical and practical knowledge by simultaneously addressing the queries of our teammates. So thank you so much, sir, for investing your time, even though you are not feeling your best today. And we would like to have more and more sessions in future also with you, sir. Thank you so much, sir, once again.
Thank you. Shall I leave?
Okay.
Yes, sir. Thank you so much, participants, for your patience listening. Uh, Feedback link and attendance link is already posted thrice in the chat box. Kindly check it once. And tomorrow we have two sessions. Session 9 by Dr. M. Venkatesha sir. He's a professor and HOD from Sai Vidya Institute of Technology. And the topic is research trends and methodologies in quantum and photonic technologies. And this session followed by session 10 by hands-on session hands-on training of AI by Dr. Ashraf Ali. He is the director, BIS Technologies Private Limited. If you have already submitted the feedback link and attendance link, you can leave the meeting. Once again, thank you so much, guys. Have a nice day. Take care.